this lecture we continue the discussion on the exercise on production flow analysis. We also try and see some aspects of reducing intercell moves, and we would also like to see how the rank order clustering algorithm works. In the previous lecture we started this exercise on production flow analysis by considering this machine component incidence matrix, where the requirement of machine on components was given in the form of workload of equivalent number of machines. For example, this number 10 indicates that component number 1 visits machine number A and requires 0.1 or 10% of machine capacity. So, starting with this matrix, we converted this to a 0-1 matrix, which we are familiar, and we carried out, we developed or created the frequency table. From there we identified the modules, and from the modules we identified a final solution. Assuming 85% capacity, we defined two solutions. One solution where we did not consider or create any intercell move, and we ended up saying that we would require 8 new machines when the existing machines are divided into 3 cells. This was the final solution with 3 cells, with machines A, B, C and G in cell number 1, A, B, C, D, F, H in cell number 2, B, D, E, I, J in cell number 3, making the corresponding components. The number before A, that is 2A, would indicate that due to capacity requirements and demand of the components, we would require 2 units or 2 copies of machine A in that cell. So, this gave us a solution considering the available machines and the required machines. We said that 8 new machines are required. The problem also tells us that each machine costs 20 lakhs for the sake of illustration. So, we have one solution with no intercell move, with more duplication of machines, which would cost us 160 lakhs. Now, we considered another situation in case we felt that buying 8 new machines was not possible or it was too expensive. One would try and reduce the requirement of the extra machines by creating intercell moves. So, we gave another extreme solution with no extra machines bought. If you see carefully, the requirement and the availability match for A, B, C, D, and E, F, G, H, I, J, the requirements at an aggregate level match, because certain machines are or can be used interchangeably. So, this solution gives us no extra machines, but 8 intercell moves. This solution also forces us to have or to accept 100% utilizations and so on, but it gives us a solution with 8 intercell moves, which would cost us 4 lakhs. The problem states that each intercell move would cost us 50,000 rupees. So, we have two extreme situations, one with 160 lakhs and the other with 4 lakhs. Now, let us look at another solution to this problem. Now, when the same exercise was carried out in a class as a class exercise, the students worked out production flow analysis. The students created these 3 cells and modules at the end with the corresponding components given here. We have already seen that up to a point the production flow analysis algorithm is very consistent. Up to the point where we create the nucleus machine and the modules based on the nucleus machine, the algorithm is the same. We also have a step where we merge modules depending on whether one of them is a subset of another or not. So, when we implement that step of the production flow analysis algorithm, we could merge in multiple ways, and therefore, the solutions can be different for different people. The PFA algorithm that we have seen does not allow us to merge two modules unless the machine set in one of them is a subset of another. Sometimes we may have two modules, each say having 5 machines or each having 6 machines, with 5 machines common in each and 1 machine different in each. For example, we could have a module that has machines A, B, C, D, E, F, and there could be another module which has machines A, B, C, D, E, G. Let us assume that F and G are not interchangeably used in this case. So, F and G are different machines. Now, the module A, B, C, D, E, F will have certain number of components. The module A, B, C, D, E, G will have certain number of components. Ordinarily, the production flow analysis algorithm does not permit us to merge these two, because one is not a subset of another. Sometimes while working out, one would be tempted to say, why can't I try and merge and create a new cell with A, B, C, D, E, F, G and merge these. So, it is possible to do such a thing, and the students came up with a solution which is like this. So, the final solution had 3 modules, with one of them having A, B, C, D, E, F, H, and many components visit that cell. So, we see now that 11 components visit that cell. The other one is B, D, E, F, I, J, where 5 components visit, and the third cell has A, B, C, G, which has 4 components visiting. Actually, if we go back and realize and see one aspect of this formation, we have earlier said that E and G are interchangeable. So, it is actually possible to merge modules 1 and 3 also and create a very large cell, but let us not do that. Let us consider the solution as it is, with 3 modules or 3 final cells with this machine and part family configuration. So, what we have done now is we have gone back to the original matrix and we have done this capacity assessment check, and then we realize that 2 machines of A, 2 machines of B, 2 machines of C, 2 machines of D and 1 of E, F and H are required in the first cell, and so on. The other 2 cells do not require additional machines, which is somewhat understandable by the fact that a large number of components visit the first cell. So, it might require more capacity. So, one could have a solution like this. Now, once again, if we go back and see the number of extra machines, we require a large number of extra machines. So, if we want to reduce this requirement of extra machines through the creation of intercell moves, then we carry out that analysis. If we look only at extra machines, this solution would give us 7 new machines at a cost of 140 lakhs, which is slightly different from the earlier solution, which when we considered only extra machines gave us a solution with 8 new machines and 160 lakhs. Now, let us try and reduce these extra machines by creating intercell moves and take it to the extreme end, where we see how many intercell moves will we have if we do not want to include extra machines. So, when we did that analysis, we did all the calculations and later we found that we could have 7 intercell moves with a cost of 3.5 lakhs as an extreme solution. But once again, one of the cells is showing about 100% utilization and so on. So, let us assume that the availability has been factored in the denominator and therefore 100% is acceptable. So now what have we seen? Now we have seen 4 different solutions to the problem, 2 of them that do not allow intercell moves, but require 8 new machines versus 7 new machines. So if we place a condition that not having an intercell move is foremost in terms of importance, because cellular manufacturing is all about ownership and responsibility, creating an intercell move and making a component visit multiple cells is going to take away the ownership of that component, because the ownership may be with one cell, but it visits some other cell. So it would be an unwanted component in the other cell, or another cell has to process that component even though that component is not owned by that cell. Considering this, if we take a stand that we are not going to create intercell moves at all, so we could choose between the solution which has 7 extra machines and another solution that has 8 extra machines. So given 2 solutions, our tendency would always be to choose a solution which is less costly. So ordinarily we would be tempted to look at that solution which has 7 new machines rather than a solution that has 8 new machines. Now let us look at those solutions. This is a solution that has 7 new machines, and we realize that one particular cell actually has 11 machines in that cell. So it is a large cell where more than 50% of the components are going to visit. On the other hand, if we consider that solution which has 8 extra machines, now we realize that the largest cell in terms of number of machines has 8 machines and not 11 machines, 8 machines. The other one also has 8, the third has 6. And in terms of number of components visiting, there are 7 components visiting in one cell, 7 in another and 6 in the third. So in this solution, the cell sizes are comparable, the loads, assuming that the volumes are reasonably comparable, the loads on each of these cells in terms of number of components visited is balanced, but this requires 8 machines. The other solution has one very large cell which has about 11 machines, where 11 components visit, and the other 2 are comparatively smaller with fewer components visiting them. So the load distribution is not as balanced in this configuration as it is in the earlier one. So even though the earlier one has a requirement of 8 extra machines, one can prefer the one with 8 extra machines, so that the cells are balanced in terms of workload, in terms of number of components visiting, and in terms of number of machines. So cost minimization should not and need not be the only consideration in cell formation. Other aspects such as not having intercell moves, understanding the importance of ownership and responsibility, not creating or not allowing components to move from one cell to another, which is intercell move, understanding the size of the cell, understanding the workload on the cell in terms of number of components visiting, they are all important and have to be given due consideration while creating manufacturing cells, and one should not go entirely by a cost minimization approach. It is also important to consider a revenue maximization approach, where each cell could be considered as a factory within a factory or as a profit center which is earning revenue to the organization. So one could look at an aspect where what is the percentage of business that comes out of this cell, and it would also be good to create cells such that the amount of business that comes out of these cells is also reasonably balanced, so that one cell does not dominate others in terms of contribution to the profit margin. It is certainly not a bad idea to consider that. Many organizations do that. At the same time, one has to give due consideration to aspects such as cell size, cell load in terms of hours of requirement, the ability, the amount of control and ownership one can have. The smaller, small is beautiful, so smaller the cells are, more control one could have. So one could think in terms of creating a slightly large number of small sized cells rather than a small number of large sized cells. So all these considerations have to be made when these manufacturing cells are formed. So let us look at some inferences that we have made through this particular example. The first one I did speak about, which is large cell size versus fewer extra machines. The solution that we saw in the second case is the one with a larger cell size, which is here. In fact, we should see this. This is the larger cell size, and this is an example that required fewer extra machines compared to the other one. Extra machines versus intercell moves. This solution is also a pointer that we have more machines in the cell, even though it requires fewer extra machines. There is one very large sized cell. So when you have large sized cells, they will have the ability to absorb a lot of workload within that cell, and therefore they will minimize the intercell moves. That is why this solution gave us 7 intercell moves. Gave us 7 intercell moves as against 8 intercell moves in the previous case. Of course, we did talk about reducing intercell moves, which is the prime importance here. Most importantly, bringing the intercell moves to 0 is the ideal situation, and it is the situation to which cell formation has to be geared to. When we are sitting down to plan a cell or to form a cell, one should always keep in mind that we should not try and create intercell moves, and if such a thing is not possible due to other cost considerations, then we should try and minimize the intercell move creation as much as possible. Now there are certain other ways by which intercell moves can be minimized. Now we will also look at this aspect as we move along in this course at some subsequent point, but there are several things that people have considered to actually reduce the intercell move. Now let us look at this matrix where we have shown explicitly some intercell moves. Let us look at this matrix which we have already seen. This is the final structure in the first example that we saw in production flow analysis. Now if we assume that we have sufficient copies of 6 and 8 such that they can be added to multiple cells, this solution has only 2 intercell moves, where component number 2 goes to machine number 14 in a different cell, and component number 9 goes to machine number 11 in a different cell. Now when we have this kind of a situation with intercell moves, how do we reduce the intercell moves? So first and the simplest one is called machine duplication. Now from this matrix, if this machine number 14 right now belongs to this cell, now if we buy another machine number 14 and add it to this cell, then this intercell move will be eliminated. which means this one will go into the cell. So, first way by which one can the easiest one can look at is machine duplication. In fact, even before machine duplication, one has to see whether is it possible to change the process plan or to change the order of visit of the machines. First, to check whether any one of these 1, 2, 9, 16 and 6 and 8 which belong to this cell, whether any one of these 6 machines can actually do this particular operation. Now, the reason I am talking about this is because if we go back to how the machine component incidence matrix was created, we said look at what is happening currently and look at every part that visits machines in the company or in the factory, and then try to see what are the machines that each part or component is visiting. So, in the present scenario, component number 2 may be visiting 14 for some particular operation. If that operation could be done in machine number 6 or 8 or 16 or 2 or whatever which is inside, then automatically this can be eliminated. So, the simplest thing first is to look at, can we make some minor changes in the process plan, or can we look at existing machines in a cell which can carry out that operation. Second is to make some minor changes in the process plan so that it can be done in an existing machine. The third of course is machine duplication. Now, can I duplicate machine number 14 into the first cell also? Obviously, machine duplication is expensive because new machine would cost a lot of money. Sometimes it is also said that we can actually buy a slightly less expensive version of that machine with less features, just sufficient to meet the requirement of this operation. Ordinarily 14 may be capable of doing many other things. If you see carefully, 14 is capable of doing even these operations, but then right now we do not need that in this particular cell, because we are interested in this particular operation of component number 2 on 14. So, try and buy a less expensive version of 14 such that it can handle the current requirement. So, that is called machine duplication. The other one is called part subcontracting or component or operation subcontracting. Now, can I take out this component entirely? Can I take out this 2 entirely from this cell and subcontract it outside? Take it to another person, another organization, subcontract it, get part number 2 as a subcontracted item which is bought from a subcontractor. Sometimes subcontracting the entire component may be an advantage if it is a standard component or part, but if it is not a standard component or part, then subcontracting would be more expensive, because component number 2 right now is being done within the factory, and if what is done within the factory is given to somewhere outside the factory, it is done and brought and bought from a subcontractor, the cost that we are going to incur is always going to be higher to when we buy something compared to when we make something. Therefore, the expense will be higher. More than the expense being higher, the control we will lose, particularly the timeliness of deliveries. The outside person may not deliver in time, may not be able to understand the daily requirements or requirements on a daily basis, which would lead us to have a little more inventory of that component, so that in case the present consignment does not come in time, we could fall back on the inventory and use it. So, part subcontracting is an alternative, a slightly less expensive alternative than machine duplication. At the same time, we lose a little bit of control because we do not have the control of making this particular component. Sometimes only operation subcontracting is resorted to, where only for this particular operation it will go out to some nearby place and it will come back. But any form of subcontracting, either entire part subcontracting or operation subcontracting, we will lose time, we will lose ownership and control of that component, which many times would either lead to a delay, and to offset that delay we would create extra inventory of that in the shop. So once again, having less inventory is an essential requirement of manufacturing, and therefore we cannot afford to create a system which deliberately increases the inventory. So typically 4 aspects are seen to minimize intercell move: to check whether an existing machine can do it, to alter the process plans and design a little bit so that an existing machine can do it, duplicate an existing machine or buy a less expensive machine and put it in that cell, and 4 is subcontract the part or operation depending on the requirement. So these aspects are seen as solutions to minimizing intercell moves. Then we get into one more aspect, which is called cost versus utilization. Now once again let us go back to these 2 solutions. If we consider this particular solution, we have 2 solutions there. One is a solution where we buy 7 new machines and spend 140 lakhs with 0 intercell move. The other is to look at no extra machine, 7 intercell moves and a cost of 3.5 lakhs. Certainly we would expect the utilizations to be much higher in this case and the utilizations to be lower in this case, because there are extra machines which have been bought, there is excess capacity, so we will have less utilization. So with an idea of eliminating intercell moves and creating more control, ownership and responsibility, some of which can be measured, some of which are difficult to measure, we could propose a solution that requires 7 new machines. But then when we spent so much money, we realize that the utilizations are very, very less. So somewhere we would then start thinking, can I reduce the number of new machines by 1 and create an intercell move, because one component can go to another cell, that cell has extra capacity. For example, in some of these computations we have shown that machine A in this cell has a requirement of 0.91, which is 91%, this is 55%. So one intercell move can go. If there is an intercell move that involves about 20% capacity, we can push this and say this will become 71, this will become 75, but we create intercell moves. So what will happen is there will be an imbalance in terms of utilizations. Some machines will have higher utilization in some cells and some machines will have lesser utilization in some other cells. So one has to understand the effect of cost versus utilization. There is one more aspect that I would revisit here. We had spoken about volume and variety. We have said that cellular manufacturing, it becomes a little difficult when we have to handle volume and variety. Now we have also seen how these numbers have been generated. This is the starting incidence matrix for this example, and we have said that this 10 indicates that component number 1 on machine number A requires an equivalent of 10% capacity or 0.1. We have also seen the equation or formula to calculate that 10%, which is Pij into Dj by Ai. So let us spend a little bit of time on this Dj in particular and see the effect of that on increased volume and variety. So, we have this formula Pij into dj by Ai is equal to Aij. So, this we can define as load on machine I due to component j. Now, let us look at how we calculate this Aij. Now, this Aij is calculated using this formula. Now, this is the unit processing time which we can safely assume is not going to change drastically with respect to time. Time taken to make one piece of this component on this machine or the machining time required is not going to change drastically. This let us assume is the available time on the machine. Now, this was calculated on the assumption that we work 2 shifts a day, 16 hours is available 6 days a week into 52 weeks. This also will not change very drastically unless there is the organization starts working in 3 shifts and so on, or the number of days suddenly becomes 5 days from 6 days and so on. Now, what is this? This is the demand or the volume. Now, let us say that we are going to start creating manufacturing cells now, which means let us say we do it in the year 2011. Now, what is the value of dj that we will assume in this calculation? Let us do this for A11, which is shown as 10% in the matrix, component 1 visiting machine 1. So, demand of component 1 or volume of production of component 1 is required. Now, what we can do is now this is the volume required. So, we could go back to various products that are made and find out which of these products require this component number 1, and from the estimated demand for these products one can find out the actual requirement of component number 1. Now, let us assume that there is a forecast of sale or production of each of these products. So, ordinarily we would expect the production to increase, sales to increase and the organization to grow. Now, just for the sake of illustration, suppose we say that the forecast for this year is 1000 for the first component, next year it is 1200 and the third year it is 1400. Now, if we assume that this cell will have a realistic life of 3 years, then the dj will be taken as the average of these 3 numbers, which will be about 1200. So, we would use the average into this calculation and then say that we would require say 10% of this. Now, let us assume that we have done that kind of an exercise and we have said that for each of these components that visit machine number A, these numbers are calculated and we say that the total requirement is 146 of A. Now, this total requirement has been considered when we did these kind of exercises. So, this 146 of A is now split into 91 of A in this cell and 55 of A in this cell. Now, let us assume for a moment that this 91 and 55, which adds up to 146, comes out of considering the average over 3 years of the production, estimated production for all the components that visit machine number A, based on which the 146 number has been calculated. Now let us say we create these cells and now we start working on these cells. So what is the requirement for which we have calculated 146? 146 comes out of this average. So in the very first year we will not be producing the average, but we could be producing lesser than the average. Therefore the requirement is actually not 146, but less than 146. So we will see that the cell is actually far less utilized than we had actually planned it for. So the underutilization will strike us to begin with, saying that we seem to be utilizing it less. So automatically we will start getting more business and then the business will increase. Now as the age of the cell increases and we move into the third year, now the workload will not be this 1200, but the workload will be 1400. Therefore the 146 that we calculated using the 1200 will be more than 146, let us say it will be 160. Now this 146, which is split as 91 and 55 here, can become 110 and 60 to get 170. So suddenly we realize that the same cell which did not have that much requirement now has more requirement. At the same time we also understand that we cannot change the cell configuration. So again what we will do is we will have no other alternative but to start looking at other places where machine A is available and we start creating intercell moves. For example, if this 91 becomes say 110 and 55 becomes 65, that 10 we certainly do not have capacity because we have only one machine. So automatically we will send that much of intercell move to the next cell because some capacity is available. Now the moment we start doing that, that is going to hurt us for many components and many machines. So once again, in spite of the fact that cells have been created, with time we will be creating more and more intercell moves and the cell will start behaving exactly like how it behaved in the functional layout before the cells were created. So that would tell us that the time has come to reconsider the cell formation and recreate manufacturing cells. If instead of a 3-year period, if we had taken a 5-year period, then once again the moment we cross the average lifespan of the cell, this thing will start hurting us because the volume and the requirement is increasing and this will start showing that as if we have less capacity. We might even be thinking while creating the cell, oh did we make a mistake by considering the average, we should have considered the maximum. But then if you consider the maximum of these and start creating this number, if you start doing this 1400, then straight away your 146 would not become 146, it would have become 160 or 170. So right at the beginning we would have added one more machine when it was not required at all. When the utilizations were about 80%, we would have 2 machines which would give us 200%, and we would not have wanted to spend that kind of extra money on the cell. So this kind of a trade off between cost versus utilization will be there right through. But in spite of that, we will have to understand that cells will have larger capacity than required for multiple reasons. In a functional layout, we had machines which could do the same or similar things were grouped together. So even if there is uncertainty in the demand, or suddenly the demand of one particular item goes up temporarily, there will be enough capacity in the department to absorb that extra demand. whereas when you put them into cells, now this, if the demand shows uncertainty and increase because of uncertainty, now that uncertainty is going to affect multiple cells to which components of those products visit, and the ability to absorb the increase is less. Therefore, manufacturing cells, when they are created, have to be created with additional capacity, and because they are created with additional capacity, they will always give us an impression of lesser utilization, because it has a little more capacity than required. So, one should again not go only by considerations of equipment utilization if we are creating cells. Now, we have seen earlier that we should not go only by cost considerations when we are creating cells. Now, again we should not be going only by utilization considerations, because a cell is expected and will show a lesser utilization to begin with, and as we progressively move with volumes increasing, it will show less utilization. When variety increases, because of which the demand on the cell increases, the effect is more compounded. So, we add both and say impact of volume and variety on the cell. So, these are some aspects that one has to understand when we do line analysis in particular. Now, variety can result in creation of new cells or having to revisit the cell formation, while volume will impact only at the line analysis, variety will impact at the group analysis, and we need to understand that aspect also. Now, let us come back to couple of discussions as we close the thing on production flow analysis. These are the additional points that we have to look at. Now, does production flow analysis give the best solution? Production flow analysis gives us a very good solution. Number one, it is easy to understand, it is easy to implement, it can even be done with a pen and pencil by hand. It does not require sophisticated algorithms to do that. Therefore, it can be well understood and done by the practicing manager himself or herself. So, the decision maker enjoys the liberty or the ability to make the decision himself or herself without falling back on additional expertise, because the method is very simple. It gives a solution, it actually gives many alternative solutions, many alternatives, alternate solutions and alternatives. Alternate solution in the sense that we saw in the same example that we saw, we had 4 different alternatives and 2 alternate solutions to choose between a solution with 8 extra machines and a solution with 7 extra machines. If we allowed a large cell size, 7 extra machines is a good solution, otherwise the 8 one. The alternative is to go for a solution with 0 intercell move versus a solution with multiple intercell moves and 0 extra cost. So, it gives a variety of situations to choose from, which the decision maker would be very happy to do, to involve himself or herself and choose the solution. But does it give the best solution? What is the best solution? How do we measure, on what parameter do we measure that this solution is better than the other? One could say that if we went only by intercell move, we would say the one with 7 intercell moves is better than the one with 8 intercell moves. But again we added another parameter and said cell size. So, how does one define the objective function or the objective that we are trying to minimize or maximize? Should we look at other alternatives other than production flow analysis? Is there a role for optimization, which is the third point that I have written. Second is, do we have an algorithmic version for production flow analysis? On one hand, the fact that PFA, when executed as an algorithm, as a method to get machine cells and part families can give different solutions with different people. How consistently can we get a similar solution? There are times we want a consistent solution, there are times we want alternatives. So, can it give us a consistent solution? Is there an algorithmic version to do the two extra things that we did? Up to the point where we actually merge, the algorithm is very straightforward. After that, we did two things. We looked at each one of the merged modules, and then we looked at the incidence data of that module, and then looked at can we reduce the number of machines by creating intercell moves. So, a thumb rule could be, if I can save one machine by creating one intercell move, I will go for it. But if we have a situation where you have to create two intercell moves to save one machine, do I go for it or I do not go for it? We also had another step where can I, by creating intercell moves, eliminate an entire cell or module. How do we bring these two into an algorithm that will consistently give the same solutions? So, which is another aspect of PFA that we have to look at. Third, but not the least, is can we look at some kind of an optimization? What is my objective function? Is there scope for mathematical modeling or mathematical programming or operations research tools? Now, can we look at the cell formation problem? Production flow analysis can be seen as a cell formation problem considering a binary incidence matrix, a 0-1 incidence matrix. Now, if we start looking at a 0-1 incidence matrix, we are essentially doing something called block diagonalization. For example, production flow analysis is still seen as one way by which we start with a matrix like this and we end with a matrix like this. This is called a block diagonal structure as written here. So, we have essentially block diagonalized this 0-1 matrix. So, the 0-1 matrix, the block diagonalized means now the rows are given in a different order, it is not 1, 2, 3, 4 up to 16. The columns are now rearranged according to a different order or a different permutation of these numbers, and the entire matrix is rearranged depending on the row permutation and the column permutation. But what has happened? The matrix takes what is called a block diagonal structure. If you see the diagonals, all the ones are now coming towards the diagonals, all the blanks or the zeros are essentially moving away from the diagonal, and the diagonal has blocks. Now, we have to imagine that 6 and 8 have been adequately duplicated here, so that they do not appear, all these do not appear as intercell moves, all these also do not appear as intercell moves. So, they will now go into the diagonals, because if we add another 6 here, then all these will go into this block. If I add another 8 into this cell, all these will go to this block. So, finally, only these two intercell moves will be outside, rest of them will go into the diagonal blocks. So, we do what is called block diagonalization. Now, block diagonalization is a reasonably well researched problem in operations research and quantitative methods. Can we block diagonalize a given matrix? So, production flow analysis, if we look at pure mathematics of PFA or computation of PFA, is essentially trying to do a block diagonalization. Now, can we apply some block diagonalization algorithms into this idea to manufacturing and see how well they perform? So, a few algorithms were implemented, which were algorithms like rank order clustering, which is particularly a block diagonalizing algorithm. So, we will see rank order clustering as we move along. Now, by merely looking at the matrix, one will understand that if I take these two rows 2 and 9, if these rows are similar in terms of matching of ones and zeros, they will ultimately belong to the same cell. So, can we have a similarity and through a similarity get machine cells? So, we go towards similarity coefficient based algorithms. Last but not the least, after all, given a set of machines, I am trying to get groups of them based on some criteria. Given a set of components, I want to make groups out of these components based on certain criteria. So, can I model it as a grouping problem? Now, grouping problem in multiple forms exists in operations research. So, is there scope to develop algorithms involving operations research and exploiting or considering the idea that we are making groups of machines and components. So, we will look at all the three aspects in the lectures to follow, and in the next lecture we will look at rank order clustering, which is essentially a block diagonalizing algorithm for binary matrices.